If, if anyone wants to have a attendance certificate, he should sign over there. So this is the first thing. The second is it's my pleasure today to introduce Andrés Castellanos. It's difficult to introduce, but in any case, he makes a PhD at la Universidad Autónoma, and at that moment there was the revolution of graphene, so he was working in the electronic properties of graphene, and then after his PhD he moved to Delft University, and he keeps working in 2D materials, but not just in graphene, but also semiconductors and other, any kind you can exfoliate from a mineral. So after the postdoc, he came back to the campus, now to the India Nanociencia, when he spent several years. And then in 2017, we were very happy because he came here to the institute with us. So he's an expert in 2D material with electronic, mechanical, and optical properties, also transport. Has a large number of papers with a huge number of citations. And one thing that several people told me that this is very ingenious in the lab, so I suppose it's true. I should mention here that he obtained 3 different ERC. One is a starting grant, a proof of concept, and the synergy grant. What else? You want me to say anything? Okay.
It's fine.
And now he's going to talk us about the roll-to-roll of 2D electronics.
Thank you a lot for the introduction and for inviting me, twisting my arm actually to give this seminar. So we are always, everyone's so busy, right? So thanks for making it. Despite that the long weekend is already knocking the door, so thank you. No, I opened one already. This one. Okay. I'm going to talk about like this, let's say, path, no, from the simple mechanical exfoliation all the way to this new concept that we developed, this roll-to-roll mechanical exfoliation. Let's see how it works, okay? So I'm going to try to gospel you that this new method to produce two-dimensional materials is not something that we can do in our lab because we are really, you know, like advanced and we are the only ones doing it, but it's something that is really transferable to other labs and easy to implement. And I hope that I managed to convince you that it's actually worth paying an effort to it. Okay, first thing first, I start doing PowerPoint shuffling, you know, like putting slides, changing, and so on. So bear with me that I'm going to get lost at some point. And also because of this PowerPoint shuffling, I might have the risk of forgetting the acknowledgements at the end. So first thing first, I put the first slide, the acknowledgement to the group, to the Foundry group that I moved back here to the ICMM almost 10 years ago, as Luis said. So it's almost the 10th anniversary. And I have no words to acknowledge these people. So like all the time that I spend with the people in the group are the ones that makes you wake up Monday morning and having, you know, like eager in coming to the lab. Okay, thank you so much for that. Also, I have to say that the institute itself, I mean, like the whole institute is one of the most welcoming places I've been in. So that also I would like to thank the people in the ICMM. And let's go to the topic. What are two-dimensional materials? I am going to stretch a little bit the language, okay? So I'm going to talk a lot about van der Waals materials, and I might use the term two-dimensional materials, but I might actually refer to two-dimensional materials. How many of you know what graphene is? How many of you don't know what graphene is? We have like 5 to 10 zombie attendants, okay? So how many of you want 1 million euros? No, you see, I will do my best. Okay, I prepared some slides for the 2D materials introduction, but I'm going to go super quickly through it, okay? So basically, what do we mean by two-dimensional materials is this family of van der Waals layer materials that they have like the same kind of appearance of graphite, okay? So they are layered materials, But they can be completely different in terms of like chemistry and actually like the structural properties. They can be slightly different, and electrical, optical, everything can be completely different, right? So in the same family, you have graphite and you have talc, right? And you can find these materials in completely different applications. What makes this to be a materials family is the fact that they share this thing that is very important in common. They have strong bonds in plane, and they have no dangling bonds out of surface, okay? So out of plane, they don't have any dangling bonds, and therefore, the layers, they can interact each other only through weak van der Waals forces, and therefore, it's very easy to cleave these materials, okay? Fine. How we cleave these materials? Now we have to talk about different production methods. And as the title of the talk says, so we're going to go from the Scotch tape exfoliation to the roll-to-roll, and the old Scotch tape exfoliation, okay? So for those you're not familiar with, this is the kind of tape that we use for exfoliating two-dimensional materials. This is not the normal magic tape, 3M magic tape. This is called Nito tape, but this is the thing, okay? So this is a career-making thing, okay? So you can get tenure, you can get everything out of just exfoliating layer materials with the Scotch tape. The best material quality that we have in two-dimensional community so far, actually I'm going to pass the tape so you can, yeah. So the best quality material, it is produced these days, still these days, with the Scotch tape exfoliation, with this Nito tape exfoliation. Still nowadays, there is no other method that can, overcome the quality of the crystals that we fabricate with this material, with this technique. This very simple technique that can be replicated in every lab all around the world, okay? So then the question is simple and clear. Why do you want to move on? Andres, you made all the career out of this. So you're making good devices. You can do like really fancy devices, strain-tronic devices, photodetectors, field effect transistors, and they have like really good performance. So why do you want to move out of that? No, so like keep doing mechanical exfoliation. The answer is that, of course, I mean, like there is nothing as a perfect production method, and this is true for any materials family, right? So like there is no one method that is like the method to grow this thing. No. There are methods that they are good for certain things. And mechanical exfoliation, manual mechanical exfoliation with the Scotch tape, the adhesive tape, it is only good for science, okay? So we can do exquisite devices, so excellent crystals, but they're only going to be good for the lab. They're going to be completely useless in any other market, okay? And the reason is because scalability, control, and integration, it is a hassle. So you cannot have like, 10,000 students exfoliating with the Scotch tape and doing deterministic transfer in order to do a real device. I mean, it's out of the question, right? Because of ethics, I guess. So Novoselov already realized that indeed, so you can always plot these kind of like matrices, right? So like different production methods for two-dimensional materials. And one easy way is to plot quality against the price of mass production. Because mechanical exfoliation is really easy and really cheap to fabricate. But the problem is that it's good for just a small production. If you want to do this in large scale, then the price is rocket high, okay? Out of the different methods to produce two-dimensional materials, liquid phase exfoliation or liquid-based exfoliation methods, they allow for this kind of like super large scale and low cost, right? So they are easy to integrate in the, let's say, production chain in the industry. But the problem is the quality. So the quality of these kind of like liquid phase exfoliated films produced with, inkjet printing, spray coating, and so on. So the quality is still way underneath the one that we get with mechanical exfoliation of single crystalline flakes. If we go to the physical vapor methods, chemical vapor deposition, or the composition of silicon carbide, these methods, they allow for wafer scale, they allow for homogeneous kind of like thin films. The performance, they are much better than the one that you get with liquid phase exfoliation. but the cost and complexity to integrate in production is high. For example, all these methods, they typically lack of integration with the CMOS compatible line of production because of the temperatures that you need and the metals usually you need to use for the chemical vapor deposition and so on, right? So what we want to do is literally taking the mechanical exfoliation and bringing it all the way here in price. We want something that produces crystals with the quality that we get with the Scotch tape, but that we can scale up so that we can produce in large scales with low cost. Okay, that is the ideal thing that we want to do. And this is what this roll-to-roll mechanical exfoliation is going to be all along this talk. Okay? I didn't say anything, but you can stop me at any point, okay? So, yes? Arc discharge is typically not used for two-dimensional materials. It's used for nanotubes, fullerenes, and all these things. If you produce platelets, they are typically very small in lateral size. Therefore, if you make a thin film, it's going to have basically the same problems as, it's going to have the same problems as liquid phase exfoliation. Yeah. All right. So, scaling up. So how we can take this kind of mechanical exfoliation with the tape, and we can, you know, like scale up all this process that we do, the peeling off the layers and so on with the Scotch tape. So we are ingenious in the lab. So this was me like 3 years ago trying to test this concept of roll-to-roll exfoliation. So I just took 2 cylinders, I coat them with the tape that we use for the exfoliation, drill, and okay, so this seems promising. So next step is to take the guys, the ones that they do the heavy lifting in the group, right? So these guys, they made the real thing, right? And it's working like a charm. And these days we have a kind of like a first prototype version that looks like a real thing already, okay? And in the following, I'm going to go through the slides to explain you how this actually works, okay? The process is very simple, okay? It's actually very simple. So we have 2 cylinders, okay? We coat the 2 cylinders with double-sided tape, okay? And then on top of this double-sided tape, we put this nito tape, the one that you're passing through, right? So the one that you have in the audience. And basically, we put these 2 cylinders coated with this nito tape to roll each other. And one important thing is that these 2 cylinders, they have perimeters or diameters that they are 2 big prime numbers, okay? This one 53, this one 23. And I'm going to put you 2 assessments in the 2 homework in this talk. This is the first one. If you don't get why it's important to have 2 big prime numbers in the cylinders, I recommend you to go and read a little bit about the periodical cicadas in the US. It's a really interesting story. All right, so we have these 2 cylinders, that they are 2 big prime numbers. They're rolling each other, okay? And what we do is, before starting the rolling, we just place a single crystal or a bulk single crystal in one of the cylinders, and then we start the rolling thing. And the rolling thing is going to basically cleave the crystals and get spread all over the tape. Actually, it's because of these big 2 prime numbers that we get an homogeneous spread, okay? So I'm giving you already some hints. And the process right now looks a little bit like this. So when you do the rolling, you start getting like crystals being cleaved and spread out all over the tape. And we included this lateral movement, this lateral sliding stage, in order to get even more homogeneous over this axis of the tape. No? So basically, if you take a look to the tape, so it looks like this. These parts are crystallites of van der Waals materials being exfoliated. Without the slider, you get these kind of like fringes. Okay? So basically, when you finish the roll-to-roll exfoliation, you get the tape, and this thing is a film full of crystals that they have been exfoliated of this parenting flake. Okay? So when you take a look in the optical microscope, you see that, okay, this is not just a single crystal that we get, okay, that is covering the whole tape. It's a network of flakes. And there is a little bit of gap in between some of the flakes. So there is a little bit of touching, a little bit of gap, okay? So it's almost complete coverage, Okay, so it's typically like around like 90% coverage, something like that, 80, 85, 95, depending on the starting conditions and how much you do the rolling, et cetera, et cetera. But if it's in the tape, it's useless. So we have to find a way to transfer these crystals out of the tape and do in our devices. That is what we want to do. And there is a very simple method, actually. It's a thermal release transfer. So nicely enough, this Nito tape, if we heat it up to 100 degrees, it loses all the tack, all the adhesiveness, okay? So then we take the tape containing the film that we exfoliated. In this case, we put here moly-disulfide film. We attach it to the target substrate. We heat it 5 minutes, 100 degrees. And then when we peel off, basically almost all the flakes on the tape, they get transferred onto the surface. So basically, this peeling off process looks a little bit like this. So you see here, this rectangle is where the flakes have been transferred to this silicon oxide chip. And you see that the tape has this empty square and empty rectangle where the flakes are being transferred, okay? Yes? So it seems that the Nito tape adhesive gets sublimated somehow with this temperature. So we have done XPS measurements. Well, our collaborators in Rome, they have done XPS. If you anneal the samples at mild temperature in high vacuum for a long time, the samples, they're super clean. So they have done these XPS measurements that are very sensitive to the surface contaminants and pretty much negligible. So the nice thing, right now we can scale up all this process to 2 inches. So we have like these wafers of different materials, moly-disulfide, boron nitride, graphite. So we have all the way from a conductor, insulator, semiconductor. We can do flexible substrates as well. So it's a very general procedure, okay? And when you're into the two-dimensional materials arena, so you get obsessed about like putting things on top of other things. And this is my second assessment for today. So if you don't know, Monty Python's Royal Society of Putting Things on Top of Other Things, you have now something to watch up in the YouTube. Okay, so can we transfer, one film of flakes and then transfer another film of flakes on top, another one? This is some obsession that we have, the community working on 2D materials. And actually, we can. So we do this thermal release transfer sequentially, and we get transfer, in this case, is 1 transfer of tungsten diselenide, 2 transfers, 3 transfers, 4 transfers. And you can see in the optical microscope that if you do only 1 transfer, you see like all these bluish parts are the bare substrate, the silicon oxide that is uncovered, okay? So you see the blue part, no? So you see some gaps. You do 2 transfers, then you cover more, 3 transfers, 4 transfers, you get very good percolation, okay? So this is very important because if you want to make a film that it conducts over large distances, you really need to do several transfers in order to get a good percolation. But you can also, of course, do these things sequentially with different materials. So you can transfer a film of a semiconductor material, a film of an insulator material, and then doing your stack on demand. So we have done, in collaboration with Carmen in the group, some AFM studies to see that indeed this is kind of a, adding up, right? So like you start with 1 transfer where the average thickness of the film is like 30 nanometers. Then you do 2 transfers, and then you get around 60, 90. When we did 4 transfers, it was 110. Okay, so I mean within the experimental error, but it's kind of adding up. Okay, so you really can do this sequentially and making your film thicker and thicker. Okay, and remember, for applications, thicker films in the order of tens of nanometers, they are more interesting than actually a single layer of moly-disulfide or graphene or anything, because they are more robust, okay, from mechanical deformations, environmental, like conditions and so on. So in the films, they are rather homogeneous over wafer scale, right? So we have done this optical characterization of the film thickness, and over a full wafer, you see that there are, of course, variations in the thickness, but the average thickness is rather homogeneous, okay? So, I mean, taking into account the stochastic process of this mechanical, roll-to-roll mechanical exfoliation process. Okay. Another interesting thing that we find out during this work is that because this rolling mechanical exfoliation process doesn't involve any twisting forces, if your starting material is an anisotropic van der Waals material, like for example, in this case, we have a black phosphorus single crystal, and you can already see from the single crystal that you can see that this has two different crystal orientations. So black phosphorus has this kind of elongated shape of crystals. And now you place this elongated single crystal carefully there in the tapes, only just one single crystal well oriented on the tape. And when you do the roll to roll, what you get is a film of little flakes, but all of them, they are aligned along the same crystallographic orientation, okay? And you can easily see that basically making transmittance optical images with a linear polarizer that is being rotated. So basically you're doing linear dichroism, and you see how all the flakes, they change color at the same time. So if you plot the transmission as a function of this angle of this polarization, of this linear polarizer, you see that indeed all the flakes, they have the same periodicity with the same, so without a big shift between them, okay? So you can even fabricate electronic devices exploding this kind of inherent anisotropy, right? So we have this chromium sulfur bromide material. We have these electrodes at different crystal orientations, measured, fabricated to probe, to test different crystal orientations. And when we transfer the crystals, you basically get like all these elongated crystals here. There is, of course, some degree of disorder, but overall, if you do a polar histogram, you see that most of the crystals, they are oriented along the same direction. And then when you measure electrical transport properties, you see that indeed there is an enhanced current along this crystal direction and a depleted current along this direction, because all these flakes, they're aligned through the same direction. And this is interesting because basically this film is inheriting this anisotropy of the bulk single crystal, okay? So, but this is not a single crystal. So it is a network of interconnected flakes with a lot of junctions, flake-to-flake junctions in between, and still the overall device shows the same kind of anisotropy, okay? If you do it without controlling, yes. But if you use the same tape, okay, you know that in this tape, all the flakes, they are aligned along this direction, so you cut the little pieces of tape and then you align the thing. But indeed, if you do it blindly without, let's say, taking care of how you place the tape on the substrate, it will average to 0, yes.
And in principle, you could use the same concept to form a twisted bilayer, more or less with a control angle.
Yes, but the problem is our flakes, they are typically tens of nanometers thick. So like one transfer is typically like 10 to 40 nanometers thick, something like that. So then you can transfer two transfer films with a control angle between them.
Yeah.
Yes, so we have done that, but it's not going to help for the magic twisted angle graphene, for example, because we don't produce like single layers with this method.
Yeah, but the stacking between the two last layers will be controlled.
Yes.
Okay.
Yes.
Okay.
So you will have just at the interface the moire, because the rest is going to be relatively thick. All right. So let's see how we go. Okay. So one important thing is the performance of the devices that we can fabricate with this. No? So like, as I discussed at the beginning in the introduction, when you do this matrix quality versus price, quality is basically the performance in terms of electrical and optical properties. Okay, so this is important. So we have to make devices, right? And one of the nice things about this production method is that it allows you to fabricate devices in batch. Okay, so you can, with very simple technique, for example, shadow mask evaporation, so you can fabricate batches of 20 and 20 devices, like this is case here. There are 20 photodetectors fabricated on silicon oxide. You can fabricate many of them, and then basically you are limited by how fast you can characterize the devices, actually. So now the limitation factor is not how fast we can produce the devices or how much success rate we have, how much yield, right? So we have in the fabrication is how fast we can characterize the devices. So we fabricated 80 photodetectors. If I remember correctly, this is tungsten diselenide. And basically, out of the 80 photodetectors, there was this one didn't work. Okay, so not bad. I mean, 96% success yield. And of course, we have a dispersion in the photocurrent and so on, but it's expected from this kind of like network of interconnected flakes nature of the films. Okay, so we have to always remember that the films that we produce here, they're just the patch, a network of interconnected flakes. So we fabricated as well field effect transistors using backgate geometry, so using silicon with silicon oxide as a dielectric, and then fabricating the transistor. And this is important because in many of the low-cost field effect transistor works, so they only work well when you use ionic gating. Okay, so if you use backgating in inkjet printed, spray-coated films with two-dimensional materials, performance is, allow me to say, crap. Okay, so these are not like the greatest field effect transistors ever, but getting a mobility in the champion device of around like 3.5 centimeters squares volt per second is already remarkable. So when you compare this with liquid phase exfoliation material, spray coated or inkjet printed or Dr. Blade, all these different production methods, this number is huge. Okay, and we fabricated, of course, not just the champion device. Okay, I showed you the hero device with a good performance and so on, but we fabricated many devices. In this case, field effect transistor characterization, it is way longer, takes longer time than the photodetectors. So we were limited to 27 devices, but out of it takes quite some time to do the gate traces, the IV curves, the transfer characteristics, and so on, okay? And when plotting mobilities and when plotting the on-off ratios, you see this huge dispersion, and it looks like well, forget about this fabrication method. I would like to stress that you can get despair by this kind of like long, dispersion in the values of mobility and on-off ratios. But luckily for us, we've been fabricating field effect transistors with single flakes, carefully mechanically exfoliated, manually placed in the position you wanted. So I went all the way to Pablo Bastante's thesis, and I took, I think if I remember correctly, 10 or 12 different molybdenum disulfide single layer transistors. And you see that basically the values, they have like the same kind of dispersion. So this is more limited basically by the rudimentary microfabrication facilities that we use and the processes that we use and the lack of post-processing that we do in our devices. So basically we fabricate devices and the more advanced thing that we do is just a thermal annealing. Okay, while in the semiconductor industry, there are tons of post-processing steps that they are done actually to tackle the device-to-device variability. Okay, so when started to fabricate these kind of like batch devices, so we got also interested in, okay, so now we have like this super large area films. How can we exploit the fact that we have large films to make devices even simpler? Okay, and we happen to have this inexpensive laser engraving machine. Okay, so this is 1,000 euros, something like that, and it works as a charm to do laser ablation of the film. So this is the case of a large area graphite film on polycarbonate, and then using this laser, we can ablate the graphite from the regions that we don't want and fabricate it, for example, in this case, interdigitated graphite electrodes. Now we can go to the snito tape. We can do squares with tungsten diselenide, moly disulfide, whatever semiconductor that we want, stamp it using this thermal release transfer, and then we have an instant device. No lithography, is hassle-free fabrication of devices. So this allows you to fabricate devices without any microfabrication, any metallization, all van der Waals. Okay? So we started to think about like, okay, what kind of more complex devices we can do with low, let's say, low effort. I say, what can we afford in our group to do that is a little bit more complex than just a photodetector? So then we did these graphite electrodes, tungsten diselenide grids, stamping the tungsten diselenide on top. And then if you take a look to one of these regions here, basically you have a graphite electrode, tungsten diselenide transistor, a graphite electrode. So we have an array of photodetectors. So we have a little camera here, okay? So lithography-free, no metallization, no nothing. No ultra-high vacuum, no even high vacuum, okay? So now let's see if it works as a camera. So we take a mask with a pattern, an LED, we illuminate it on top of the device, and when we measure the photocurrent of the different pixels, we see that indeed we are able of reproducing the illumination that we are projecting on our device. So we managed to do a 4x4 sensor, image sensor in the lab, which, okay, so it sounds not very exciting, but it's the first time. I've been working on optoelectronics for many years. This is the first time that I actually did a real image sensor, okay? Okay, so now, I don't know how I'm doing with time. So I'm okay? Okay. So I would like to say how we want to integrate this in the, let's say, the plans of the group for the next year. And as you know, a big deal of the research in my group is being shaped by the Skin to Electronics project, the ERC synergy with Gianluca Fiori, with Andraskis and Kostas Kostarelos. And it is based on fabricating these electronic components that they are so floppy, so compliant, that they can, be integrated on rough surfaces as a second skin, okay? So what can we do with this roll-to-roll exfoliation within this context? Because we are going to focus a lot of, we are going to put a lot of meat on this area. So when we talk about rough surfaces, we are talking about things like wood, steel, plastic, textiles, or skin. Trust me, it is a nightmare to fabricate any electronic component that can be integrated on these surfaces. And how these roll-to-roll films can help us in this conformal electronics, I foresee two ways, okay? First one is, of course, we are making thin films, okay? So even if they're multi-layered and several transfers and so on, so at the end of the day, these devices, they can be as thin as tens of nanometers thick. And the stiffness of a rectangular plate, if your mechanics, continuum mechanics is a little bit rusty and you don't read Timoshenko in a regular basis, it goes with the cubic power of thickness, okay? So the thinner the device, the more compliant it is. This is crucial. A lot of people, they are getting obsessed about doing soft electronics and making things with the lowest young modulus possible. Young modulus is not the key thing. The key thing is the thickness. The thinner the device, it doesn't matter if it's a super stiff material. If it's thin enough, it will comply to the rough surfaces, okay? So in here, we have these thin films, we are fine. Second thing is that this kind of conformal electronics usually has to be strong against mechanical deformations. Stretchability, especially, is a difficult one, okay? Two-dimensional materials, they are inherently really sturdy against mechanical deformations. They can, so single crystals, they can survive, very big mechanical deformations. But also, these kind of films, they're, as I said, a network of interconnected flakes. So if you take a look to the cross-section SEM or top view of the SEM, you see the flakes, patchy, this kind of like surface. You can imagine that if you apply a mechanical deformation to these films, what is going to happen is that these flakes, they're going to slide against each other. Importantly, because as I said at the introduction, van der Waals materials, they don't have dangling bonds on the surface. Therefore, they have this kind of good sliding because they don't get stuck, okay? So we believe these kind of roll-to-roll films, they're going to be good for our purposes to fabricate sensors that they can integrate on rough surfaces as a second skin. So let's do it. We go to the lab, and we started taking just tattoo paper, temporary tattoo paper. The same temporary tattoo as the kids, they have these calcamonías, depending on the region of Spain, I think it's said differently. So we use the very same technology, the very same transfer paper, and we fabricated our devices on it. So in this case, it's molybdenum disulfide and gold electrodes, and then we put it on water, and then it delaminates. Okay, so we have, I think here you can see how compliant this is. Okay, so it can really cover the topography of the finger really nicely. And there are different technologies for this kind of so believe it or not, these calcamonías, they have technology behind. There are patents, there are different approaches and so on. So this is one of them. This is temporary tattoo. The other technology is water slide, decal paper. Okay, we also tried this one. So basically this one is the one we are, I think, more familiar with, is you put the device there facing down, no, upside down, and you now slide device on skin. Okay? As simple as that. Now the question is, in many of the papers in where they do these kind of conformable devices, they show you like this kind of like videos and pictures, but all the measurements, they are done on just the devices before releasing. Okay? So like the device works on the paper, but then when you transfer on the skin, does it work on the skin? If you transfer to a rough, whatever surface, does it work on the rough surface? In many of the papers in the literature, they don't test it. They simply stuck measuring like the devices on the flat surface, okay? So we tried transferring on different surfaces, and for the electrical testing, some of the students, they were really resilient against, getting probe tips, piercing their skin and so on, so, ethics and all these things. So we had to move on to a surrogate kind of surface. So we tried artificial leather. Okay, so this is our surface that we use for mimicking the skin. Okay, so then we can safely test the devices there on this leather that is kind of like similar in kind of like mechanical properties than the skin. It is also much rougher actually than the human skin. Okay, so we use this lychee pattern leather, and we fabricated, for example, few devices I'm going to show. So we have fabricated many sensors, and I'm going to show you just some examples. So a photodetector fabricated on this fake leather works as the photodetectors that we fabricated on silicon oxide or polycarbonate. So we get really fast responses, I mean, in comparison to other molybdisulfide photodetectors, that they are not the fastest by far. I mean, molybdisulfide is relatively slow. And what is important is that the responsivity of these devices reaches more than 1 ampere volt. Okay? Figures of merit, they're important in order to compare different technologies. Okay? So if you don't have figures of merit, you cannot compare two devices that they are fabricated with different material platforms, different technologies. Responsivity is one of the figures of merit of photodetectors. And to have a comparison, a commercial silicon photodetector has a responsivity of 0.1 to, in the best case scenario, 1 ampere watt. Okay? And these devices, they are already above 1 ampere watt. Okay? Of course, there are other figures in merit in which these devices are worse, but I'm not going to show them. We fabricated as well temperature sensors, thermistors, because one of the advantages of these devices is that they are semiconductor material and is an N-type with the Fermi level very close to the conduction band. It's almost, N-type dope from the intrinsic properties. So it means that a little change in temperature is enough to change the population of charge carriers just by thermal activation. And because of this nature of interconnected flakes that we have in these films, a little change in temperature as well is going to change, because of thermal expansion, the coupling between the layers by sliding, right? These two things together makes this resistance of these devices extremely sensitive to temperatures within the room temperature. I mean, if you go from 25 to, in this case, we went to 38 because it's the physiological kind of interesting limit, you see a huge coefficient, PCR, of 30,000 ppm per degree, okay? And again, if you compare this with a commercial silicon thermistor, So they are typically in the order of 100. Okay, so 30,000 ppm per degree versus 100. Okay, so yes. If it degrades on the skin. With this technology, with this temporary tattoo, yes. So a normal degradation, let's say, it's like a calcamonía. So it depends on how much you scratch, how much you shower. Yes, yes, yes. So they will be, so like if, depends on the intended use, okay? So if you want a use, for example, of 1 week, you want this to work for 1 week, without any disturbance, then you have to figure out an encapsulation route. So we are working on different encapsulation routes as well. But for many other applications, it will be like a one-use thing. Okay, so you use it, and then once you have measured the thing, then you forget about it, So it depends. But, as it is, it's like a calcamonía. So it will degrade. If you wash your hands 3 times, then it's gone. Okay. And another example I wanted to show is that we can even fabricate on these kind of super rough surfaces a very coarse field effect transistor, okay? So making conformal field effect transistors is difficult because dielectrics, they're typically a problem for making good field effect transistors. But one way to go around it is to use ionic gels, okay? So we fabricated this kind of moly-disulfide with ionic gel kind of geometry, and it works as a charm. So it works as a transistor, indeed, so you can switch on the channel, switch off the channel. The transfer curves, they're textbook almost, a little bit of hysteresis, but almost tiny, despite of the fact that these devices, they are working on this rough surface. So I want to stress that, so that in many papers, they test the transistors on the surface before peeling off and transfer to the rough surface, okay? And now we are working on, instead of using the same technology as these temporary tattoos, okay? So like now we are just grabbing the technology. So what we are doing is now developing our own transfer paper, okay? So we are developing our own transfer paper that is going to make the devices 10 times thinner, okay? And this is super important. Remember that the stiffness of the plate goes with the cubic power of the thickness. So we're talking about like 3 orders of magnitude more compliant devices here. And we wanted to test it with Cristobal. Cristobal is this teddy bear here, this gummy bear. And Cristobal undertake the terrible task of being the test subject to check how conformal these devices can be. And it worked, actually. So we fabricated this photodetector. And I don't have the plot of the photodetector working, but it was working, right, guys? Yeah? OK. With that, I just wanted to finish the talk. I hope that I gospel you that this roll-to-roll is a really good method to fabricate this kind of large area, low-cost devices that is easy to implement any other place. If you're interested about fabricating devices on batch instead of just fabricating one hero device, this is something that you can implement in your lab really easily. So far, we are scaling up to 2 inches, but in principle, there is nothing preventing us to make the cylinders bigger. They're using wider tapes, to make it even bigger than 2 inches. And the performance, to be fair, there is good enough, okay? So, of course, single flake mechanical exfoliated deterministic transfer is going to be the champion kind of device. Chemical vapor deposition is going to be better performance than the ones that we get with this roll-to-roll. But this is better, for example, than the typical films people produce with liquid phase exfoliation. So it's something in between chemical vapor deposition and liquid phase. With the advantage is that it's kind of as cheap and easy as liquid phase exfoliation, and it's completely dry. No liquid solvents, no nasty chemicals. Acknowledging the funding sources, of course, that we have to put it in case of we get an audit. And I wanted to stress that this is thank you. So we managed to develop this setup from the super crappy test that I showed you in the lab with the drill and so on, to the version that we have now, the prototype, thanks to this Prueba de Concepto from the Spanish Agency of Science and the team in this Roll 2D project is in this picture. And we have some beta testers of our roll-to-roll prototype. So we have people in Trinity College, Coleman and Nicolosi. We have people in Kassel, Claudia Vaques. We have software in Zenex software in Prague. And in Italy, we have these two guys, Gianluca Fiori, of course, and Riccardo Frisenda. And thanks to their feedback, we're improving this. So if you're at some point interested in replicating this kind of setup, let us know, because we're completely open to share. And it's always good for us to actually get more information about how we can improve the technique. With that, I would like to finish. Thank you.
Thanks very much. So it's time for question.
Thank you, Andrés, for the nice talk. So with this kind of state-of-the-art technology you have now for devices and for these materials, for the skin part, what would be the most advanced application that you can realistically see in 5-10 years?
Yeah, so basically within the context of the Synergy project, so these roll-to-roll films, they are going to be useful for the sensor part, but we need other electronic components that they cannot be done with roll-to-roll. Okay, so we need to do a heterogeneous integration between chemical vapor deposition for the logic part and this roll-to-roll for the sensors. But I'm quite optimistic that the roll-to-roll sensors, they are going to reach to the level of reaching figures of merit that they are really state of the technique. Yeah. So, and we are going to focus on strain sensors, that they are really amenable for this technology because the flakes, they can slide each other, and the temperature sensors as well because of what I said. No? So N-type semiconductor, also the sliding.
Thank you for the talk, Andrés. I want to dig a bit in the ingenious device that you prepared. And I'm wondering, I assume that the thickness of the layer that you finally get is inversely proportional to the size, the lateral size of the seeds that you use. But I don't get how come or how long you have to have it running until you fully covered it, because eventually it will be fully covered.
Yeah. So there is a point when the coverage is so large that the exfoliation doesn't take place anymore because there is no adhesive. Yeah, there is no stickiness. Yeah. So right now it is just manual, eye inspection. So when you see the film fully covered, you stop, right? And indeed, there is a relationship between the lateral size of the flakes and the thickness of the crystals that you can get. Okay, so you can get thinner films if you, for example, you do one run of exfoliation, then you remove one of the tapes, you place a blank tape, and you run the exfoliation again using one of the tapes as the source of material. So then you re-exfoliate the crystals. They get thinner, but they also get lower in lateral dimensions. So when people do this liquid phase exfoliation of 2D materials, they do this process that is called cascade centrifugation, in where they get thinner crystals, but they also get smaller in lateral size. So this is the physical version of this process. So we can make them thinner, but also smaller. Then for certain applications, it will be nice to get thinner, even though they are smaller. For electrical transport, actually, you want flakes as large as possible to minimize the flake-to-flake junctions in your device. Flake-to-flake junctions, they are a killer in all the electrical properties. Yeah. I don't know if I missed something. Yeah? Okay.
This is just a curiosity. So do you know how healthy this could be for the skin? I can imagine that since you have these patches, maybe they can go inside your skin or something. It's just curiosity.
Yeah, within our team, so Costas Costarellos in ICN2 is fully devoted to the toxicity aspects of these devices. And at the end of the day, these devices, they are unencapsulated, they are just research devices. If we, at some point, take this technology closer to real application, most of them, they're going to be encapsulated for sure.
Thank you for the talk. So the idea is each time you want to measure, you have to put some wires on it, right, and measure it. So even though it's a wearable thing, it's not wireless transmitted information, right? It's something that can be done, like the idea that you can somehow wire.
So it's not yet. But within the ERC, the idea is so one of the partners is going to develop the electronics to do RFID connection to the exterior. Yes.
Thank you very much, Andrés. Very nice talk, very nice results. So my question on these advances on the Synergy grant, so how do these devices behave with liquid when liquid is around? Because you will probably have, especially thinking about brain sensing and recording and so on, liquid will be around. So do you have any idea? Have you tested already?
Not yet. So this one's not yet. So we are fabricating as well pH sensors, and those, they work in liquid already. So and we have pretty good stability when they're in liquid. But when there are changes within the liquid, so basically that is what we're exploring right now. So we are doing specific pH sensors as well, okay? And those, they operate in liquid. So most likely, so we don't know yet, but most likely, these other sensors, for example, strain and temperature, they will be encapsulated. And only the pH, they will have an opening for the liquid to enter.
Especially because those liquids will have more things inside. It's not just water.
It is not just water, yes. No,
Yes.
so far, so with the pH sensors, we have buffer solutions with different ions and so on. So, and the devices, they're rather stable. I mean, we are measuring devices like for weeks, okay? But they're still like drift that we have to figure out because temperature also affects the devices that they are sensing pH. So we have a lot of like contingency plans. I mean, already in the proposal, but for sure we are working on that. Yes.
Okay, congratulations. Thank you.
Thanks.
So beyond sensors, is there any possibility to do some kind of energy harvesting from the skin?
Yeah. So there are a lot of people working on triboelectric generators, based on especially two-dimensional materials. They are quite I mean, quite strong in this aspect. There are also people working on the Wi-Fi harvesters. Okay, so like basically you put an antenna that actually can capture the energy out of the Wi-Fi. So it is, for example, the Wi-Fi energy harvesting is something that we are considering, but as a contingency in our plan. And we are going to explore the triboelectric generators, even if it's not included at all in our proposal, because we don't expect it for the real case application that we want. We don't expect to have any friction and so on. But I think like the technology is amenable for that, so we're going to explore it anyways.
So you mentioned collecting energy from Wi-Fi, which is microwaves. So your sensors have to be microwave tuned. I know it's only under development, but Li-Fi with visible light is going to be the next thing. So maybe you have even better chances with that. Is that on your plan?
Totally agree. It is not in our plans in principle because the final goal, if everything goes as expected, is not so the final devices, they are not just on skin, but they are going to be able of being implantable. And then we Li-Fi is not going to work. And then we implemented as a contingency plan a big antenna protruding out of the implant. Well, actually, it could be a light antenna as well, so a photodetector out of the implant. It could be.
Thanks.
Yeah. So, but we didn't consider. We considered the Wi-Fi harvesting as a contingency. But the electronics is similar, actually. So because you need to basically rectify the signal. That is all you need.
Well, let's thanks again, Andrés.
Thank you.